what I'm going to do now is going to talk about a very abstract topic of Kirchoffs Law. Okay, see, if you talk about, so this is Kirchoffs Law as seen in radiation, okay? Fundamental law. So you would study one of the laws to be the Kirchoffs Law, okay? So Kirchhoff, actually just made a generalized statement on the emissive power and the absorptive power, okay, of any body. So what he said was this, that if you have, multiple bodies, so if this is body number 1, this is body number 2, this is the emission, is not dependent on the type of body this is. It does not depend on that. What it depends on is the temperature. So if these bodies are being, flooded with some radiations, and which means they're absorbing and they are, emitting, which means they have something called as emissive power. They have emissive power, okay, emissive power, which is the amount of energy they throw out, per unit area per second. That's their emissive power. All of them are at the same temperature, okay? So these are at same temperature, and they have something called as absorptive power. So this is the amount of energy which is being absorbed per unit area per unit time. The ratio of the emissive power to the absorptive power is a constant for all the three bodies, 1, 2, and 3, right? Now, what's so great about it is the fact that the material of these three bodies is different. So, the emission and absorption powers, the first man to link these two quantities was Kirchhoff. So, the statement he makes, if you read it carefully, talks about the ratio being constant for all the objects and at a constant temperature. So far, the temperature is same. This law, holds true. So he linked the emissive power and absorptive powers and brought them together. So this was his contribution. And so this is one form of the Kirchoffs law you study, that the emissive power and absorptive powers are just dependent on temperature. And then you study, this particular equation, which is about the emissive power and the absorptive powers. Another format which you study for Kirchoff's law, and it's called the spectral format, okay? So there what they do is, they write E and it's lambda and theta, whole divided by absorptive power and lambda and theta. Now, if you compare these two, the only introduction is the introduction of lambda, okay? Which means for a given wavelength, if the temperature is constant. So this is called as the spectral format of Kirchoff's law. There is no difference between these two, but this law also includes wavelength, to be an important parameter in deciding the emissive power and the absorptive power. And then if you want to complete the Kirchoff's law, okay, the Kirchoff's law is, so you can write that this is a constant and it's equal to the emissive power of a black body, okay? So it includes the black body also, okay? And the absorptive power of black bodies is 0. So if you want to write absorptive power of a black body, just put it as equal to 1. It's unity. So that is why you just have 1 here as a ratio. All right, so all this radiation chapter, so if you want to talk about thermal radiations, okay, you talk about thermal radiations. The thermal radiation does not include everything, which is in the spectrum. So for example, if you have EM waves, and you study X-rays, X-rays are not thermal radiations. Thermal radiations are like, infrared is an example of, infrared is a good example of, thermal radiation. So just be very careful that you don't apply the concepts of, thermal radiation to X-ray or any different type of ray. Just apply this to only to thermal radiations. All right. So see, you would find different flavors of Kirchoff's law. So some people stated that, if you have an object, for example, you have an object which is absorbing a particular wavelength, then this object will reflect, emit. When I say emit, I mean re-radiate the same wavelength when it is at the same temperature as compared to the external environment. So there are multiple, ways of looking at Kirchoff's law. Some people, include only temperature, which is the standard format, that E is actually a temperature dependent function, and absorption, is also a temperature dependent. And this is a spectral format, okay? And you can see, the E by A is constant. This is also part of the Kirchoff's, law, that, and you can find some statements where it says if you have three bodies, and this body has very high E, then the A also needs to be high. So good emitters, they emit nicely, they absorb also pretty nicely. So this is yet another interpretation of Kirchoff's law. So Kirchoff's law was very fundamental to the thermal radiations, and you would find, many other laws like Wayne's displacement law, you have Stephen Boltzmann law, you have Newton's law of cooling. Many laws are available to you. Kirchoff's law was a fundamental law. Now in class 12th, you don't have too much of maths associated with the Kirchoff's law. And the only maths you need to really know is this, this ratio is constant, and the spectral part of it is also somehow out of scope, which means, if you have a situation where you put, different wavelength on an object, and the temperature is different, the absorption which you see on different temperature ranges is different. So you can find at a certain temperature range some wavelengths being absorbed and vice versa, which means at certain temperatures the same wavelengths are getting emitted. So there can be a range of temperature and corresponding wavelength available in, the spectral format of Kirchoff's law. Bit hard to understand, bit abstract, but you can keep your focus only on, the concept of E by A as being constant and is equal to, being a ratio for, and including a black body also as part of the definition, and keep the absorptive power as 1. So I hope this helps you. It was a conceptual discussion on Kirchoff's law for thermal radiations, and I hope it helped you. I conduct live classes. My number is given as part of the video you're seeing. You're very welcome to join this, and I look forward to speak to you. Drop me a message. Thank you very much for your time.